Now we'll try to understand how logistic regression solves a classification problem. Already from our previous video, we understood why linear regression cannot solve a classification problem over here, because we have two issues. Because of the outliers, this line, the best fit line, may move abruptly here and there. Okay. And the second thing is that we were trying to get an output that is greater than 1 or less than 0. Okay. So these two conditions were there. Now let's go ahead and let's try to understand. Now, as I told you that if we really want to prevent from getting an output that is greater than 1, we have to basically squash this result. Similarly, we need to squash the result over here, right? So this two squashing needs to be done. Already we know that this best fit line can be created with the equation h theta of x is equal to theta 0 plus theta 1 multiplied by x1, right? So this we have already learned in the linear regression, right? But, and this is nothing but it actually gives us the best fit line. So this yellow line that you basically see, right? This is basically given for this particular equation, but we don't want this specific equation, right? Because from here we really need to squash it, and how this squashing is basically possible, that is what we are going to see. So guys, today I'm going to introduce you to a new activation function. We also say this as an activation function, which is called as sigmoid activation. Okay, sigmoid activation. Now sigmoid activation, what is the so important thing about sigmoid activation is that this sigmoid activation is basically given by the equation 1 plus 1 divided by 1 plus e to the power of minus z. Okay, now whatever the z value is, whatever the z value is, and if I try to plot this sigmoid activation function, it looks something like this. Okay, so always remember the sigmoid activation function. If you probably try to play with any z value, okay, the sigmoid activation function that you are probably going to get, and I will probably give this denotation as sigmoid of z, right? So with respect to any z value, always remember your sigmoid outputs between 0 to 1. Okay, 0 to 1. So this is one condition, and your sigmoid activation will have a curve which will look something like this. Okay, which will look something like this. Let me just again draw it a little bit properly. So this is how a sigmoid activation function will look like. That basically means your value will always be between 0 to 1, and this mid one is basically your 0.5. That basically means whenever your z value is greater than 0, understand from this, whenever your z value is greater than 0, then your sigmoid of z, right, is always greater than 0.5. Okay, so greater than or equal to 0.5 if I say greater than or equal to 0. Okay, so at any instance, whatever z value you select and you try it out, you probably go and Google over there and you just say that draw me the curve of this specific equation, which is called a sigmoid curve, right? So this sigmoid curve will always give this, and whatever z value, irrespective of any z value, let it be a negative or positive z value, your values will always be ranging between 0 to 1. Now because of this equation, what we are going to do on this best fit line, we are just going to apply the sigmoid activation function. Okay, so that is what we are actually going to do in order to achieve this. Okay, so in order to achieve this, now what will happen is that both the problems will actually get solved since we are squashing it over there, right? So any outliers that also comes in the future over here will also be giving the output as 1. Okay, so this is how we are going to do it. Now let's go ahead and write out our all the equations that is required. Okay, now first step is that in logistic regression, we also create a best fit line, and then on top of it, we apply a sigmoid activation function. So let me go ahead and write our new function, right? So I will write h theta of x. Now always remember, when I am writing h theta of x, I'm basically going to use a notation sigmoid, because I'm going to apply a sigmoid activation function on this specific equation if I have just one independent feature. Right? If I have multiple independent features, then it becomes theta 1 x1 plus theta 2 x2 plus theta 3 x3. But let me just show you with respect to this, and you will be able to understand that. Okay. Now what we are going to do over here is that we are just trying to apply this activation function, which is basically given in this sigmoid. And here, this sigma, I am going to denote it by 1 plus e to the power of minus z. Okay. And let's consider that this specific value is z now. Theta 0 plus theta 1 into x1. Okay, so let's consider this value is z. So in short, I can basically write sigma by z. Okay, which in short I can basically write h theta of x, which is the usually whenever we, even in linear regression, right, we took theta 0 plus theta 1 multiplied by x. That is the equation. Now h theta of x, the hypothesis that we are going to apply will be basically 1 to the power of e to the power of minus z, where z is nothing but this specific value, which is nothing but theta 0 plus theta 1 into x1. Okay, x1 or x, anything, right? So what we are doing, first of all, a best fit line is getting created. On top of it, we are applying a sigmoid activation function. So always our output will be between 0 to 1, right? So this is the entire hypothesis that we are going to use. Let me again highlight it. So this is the entire hypothesis that we are going to use. So I'll just mark it like this. So this is my logistic regression hypothesis. Okay. So this is my logistic regression hypothesis. Logistic regression hypothesis. Okay. And here you know that z is nothing but z is theta 0 plus theta 1 into x1. Okay. So guys, I hope you have understood the logistic regression hypothesis as I discussed. So this is basically the equation of the hypothesis. Now what I am actually going to do is that let's go ahead and consider the linear regression cost function, and then we'll try to modify the logistic regression cost function. Okay, so I'm just going to write over here linear regression cost function. I hope everybody remembers what linear regression cost function is. Okay, because we have spent a lot amount of time in understanding the theory of that. So this is basically j theta 0 comma theta 1 is nothing but 1 by 2m summation of I is equal to 1 to m. Okay, and this will be h theta of x of I, okay, minus y of I whole square, right? So obviously you know what h theta of x is in the case of linear regression. It is nothing but theta 0 plus theta 1 into x if you just have one single independent feature. Now similarly, what I'm actually going to do, I'm going to write it for the logistic regression also. So logistic regression cost function, since we are using regression somewhere, right, and later on we are applying an activation function which is called as sigmoid. So logistic regression, if I really want to write, I can basically give the same notation over here also, something like this. So this will be j theta 0 comma theta 1, which is nothing but 1 by 2m summation of I is equal to 1 to m. Here also we'll try to use the same notation. Just a second. But what is the thing that is basically changing? It is nothing but your h theta of x. So here I can definitely write my h theta of x is nothing but 1 plus e to the power of minus z, and z is basically given by theta 0 plus theta 1 into x1. Okay, so this is how we have probably learned it from here, right? Because z is nothing but theta 0 plus theta 1 into x1. So now if I use this notation, understand what will happen. If I directly use this cost function, and inside this cost function, what is h theta of x? It is nothing but this sigmoid activation function, right? In short, this is basically sigmoid activation function. Now, can we get the gradient descent curve with the help of this particular cost function? The answer is no, guys. Why? Because this cost function, if I try to plot it with respect to theta and cost, this is going to give me a non-convex function. Okay, non-convex function, and this equation that we probably saw, this will give me a convex function. Now the gradient descent, now for this, what is the gradient descent that is usually created when you try to create a plot with respect to theta and j of theta? You will be seeing, you will be getting this kind of gradient descent, right? And over here this will basically be your global minima, right? Global minima. So this is specifically your convex function. So I really want to call this as my convex function. So gradient descent is actually a convex function, right? Gradient descent is actually a convex function. Now, if I try to use this equation that is there and try to plot it, then what kind of curve will I get? So if I try to plot it over here with respect to theta and j of theta, here you'll be seeing that we will be getting this kind of curve, something like this. Okay. And what is the problem with respect to this particular curve? It is, first of all, it is non-convex. Okay, so it is non-convex. Whenever it is non-convex, that basically means, obviously this is my global minima. Okay, but here you have some more points, and these points will basically create something called as local minima. Now, what is the importance? What is the disadvantage with respect to local minima? Because whenever I come at this particular point, and if I try to find the slope will always be 0. And if the slope is always 0, the theta will be remaining stagnant at this place. It won't be able to increase or reduce, right, to come to the global minima. So it will be very, very difficult to come over here. So this is basically my global minima. So if I probably use this equation, right, and if I try to create my relation between theta and j theta, I'm going to get this kind of non-convex function. So it is, and it is proven also, guys. I don't want to do the proof entirely and probably just try to plot with respect to each and every point, but if we try to use this, we are going to get a non-convex function. Now, in order to prevent this, what we can do is that let me again write the cost function of logistic regression. So let's say this is my cost function. Here I'm basically writing 1 by 2m, summation of I is equal to 1 to m, and here I am writing h theta of x of I minus y of I whole square, right? And obviously everybody knows what is h theta of x. It is nothing but h theta of x of I is nothing but 1 plus e to the power of minus z, where z is nothing but theta 0 plus theta 1 into x1. Right? So this we are basically discussing from that much time, right? This is very, very much simple. Now let's consider this is my cost function. Now instead of using this as my cost function, let's consider this. I'm going to indicate this as cost h theta of x of I, comma y of I. Let's say I'm denoting it. Let's denote this value as this. Okay. So what we can do in order to get a convex function, we can basically write cos theta of h theta of x of I, comma y of I can use this equation, and yes, we can also prove this, but I'm just going to write down this equation over here because the proof is not that important. If I say minus log of h theta of x, okay, and if my y value is 1, okay, so if my y value, in this particular case, if my y is 1, I'm going to use this as my cost function, which is basically going to get replaced over here. Okay. And one more condition is that if my y is equal to 0, I may probably use something called as minus log 1 minus h theta of x. And why you are using this? Because this two specific thing, this two log, we basically say this as log loss. Okay, log loss. And if you are using this log loss, this will be able to create a convex function that is basically required in terms to get the global minima. Okay, so we are going to use these two conditions over here, right? Over here, when my y value is 1, I'm going to use this equation. When my y value is equal to, I'm going to use this equation. And these two equations, when we are using with respect to different y value, we basically get a convex function. Okay, so that is what we get it mathematically. Again, I don't want to prove this as a formula, you just need to remember it. So in short, if I try to combine this, my cost, this specific value can be replaced by something like this. So I will go and replace it something like this, where I'll write cost, not cost, it is cost. Did I write cost? Cost, okay, fine. If I try to write cos, it will be cosine, right? So here I'm going to write cos h theta of x of I, comma y of I. If I try to use this log loss, we can definitely create an equation which is like y log of h theta of x of I, y log of h theta of x. Just a second. Okay, so I'm just going to write minus y log of h theta of x minus 1 minus y of 1 minus h theta of x. Now here you can definitely see that if my y value is 1, if I replace y value as 1, I'm going to get this specific equation. Okay, if I replace y value with 0, then what will happen? This will entirely become 0. This into this will become 0. So I am actually going to get something called as, see, 1 minus 0, this will be 1. So I'm actually going to get, okay, I missed one thing over here. Just a second. This equation will be changing a little bit too. After this minus, I'll be using 1 minus y log of 1 minus h theta of x. Okay, so in short, if I replace y with 1, If I replace y with 1, then I'm going to remain with only this specific equation, because 1 minus 1 will be entirely 0. This entire term will be 0. If I replace y with 0, at that point of time, this will become entirely 0, and I'll be, remaining with this specific equation. So with the help of this, what we will be able to do is that we will be able to get a cool convex function as a gradient descent. Okay, so that is the reason why we specifically use it. Now what I'm actually going to do, this entire cost function that I've actually written over here, I'm going to replace it with this specific value. So finally, my final conclusion with respect to j theta 0 comma theta 1 is nothing but minus 1 by 2m. Okay, summation of I is equal to 1 to m. Why I'm taking minus? Because here both are minus, right? So I'm going to take out this minus outside. So finally I'll be able to write y of I, okay, log h theta of x of I minus 1 minus y of I log 1 minus h theta of x of I. So this will be my entire cost function in short. Okay, so this will be my cost function. Now what do we do with the help of cost function? And always remember, this cost function will actually give us a convex function. Okay, this cost function will be actually giving us a convex function, or I can also probably call it as gradient descent. Okay, so this is my cost function. Again, the lines are not getting created properly. Let me try it out once again. Sorry for the inconvenience. So here is my cost function. Now our major aim is always to minimize cost function by changing value. So here my cost function is j theta 0 comma theta 1 by changing theta 0 and theta 1, right? So in short, if you remember, again we have to write the convergence algorithm, and then this convergence algorithm we repeat. So here I'm just going to say convergence algorithm. We are going to just repeat one important step, that is nothing but we are just going to change theta j value, which is nothing but theta j minus learning rate, derivative of theta j with respect to j theta 0 comma theta 1. So in short, we are going to find out the slope to find out the best fit line, and here your j value is 0 and 1. And obviously that derivative part, whatever we have written in the simple linear regression, that same thing we'll be writing it over here, right? So this is what we have done. You need to really understand why we did not use this specific cost function, because this was giving us a non-convex function. In order to replace this non-convex function, we used something called as log loss, and this is basically my log loss, wherein I'm using two specific thing with respect to this cos theta x of xi minus y of I. Whenever y is equal to 1, I'm going to use this. If y is equal to 0, I'm going to use this. Okay, so h theta of x is nothing but this is where I'll do the predictions, right? Predictions with respect to any value. So finally I write my cos theta of x as this specific equation. This will definitely create a convex function or gradient descent. So finally you'll be able to see that I will be writing my cost function as j theta cos 0 comma 1, and this is the entire equation. And our main aim is to minimize the cost function by changing theta 0 and theta 1, and we'll try to repeat the convergence algorithm where we'll keep on updating theta j value, and where j is equal to 0 and 1. And similarly, if I have multiple features, the j will keep on increasing, like 0, 1, 2, 3, 4, 5, 6. So I hope you have got an idea about the entire mathematical intuition and how we are using logistic regression to solve the classification problem, right? So yes, in the upcoming videos we are also going to discuss about the performance metrics. This was it from my side. I'll see you in the next video. Bye.